Okay, so postulates-2 in quantum mechanics. This postulates-2 represents the operator. This postulates-2 will tells about the observable quantities in quantum mechanics. Okay, so let us recall in classical mechanics like energy, the measurable quantities like energy, momentum. So these are all the functions of position and momentum. So right. So okay, but in quantum mechanics, these measurable quantities, measurable physical quantities, or nothing but observable quantities are represented in operators. In quantum mechanics, these measurable quantities, whatever the measurable quantities we have studied in classical mechanics like energy, momentum, angular momentum, linear momentum, so total energy. So these measurable quantities are replaced as a operators, the corresponding operators in quantum mechanics. Okay, the statement of this postulate is, see, so in quantum mechanics, okay, so in quantum mechanics, a very physical, okay, very physical measurable quantities, okay, or quantity, like which are being called as observables. Okay, these physical quantities. Physical quantities means all measurable quantities. You can call them as observables. These observables are described by an operator. Okay, and this operator must be linear and also hermitian. Okay, so what are these measurable quantities or observable quantities are described, or we can replace these observable quantities in terms of operators, but these operators must be linear and also hermitian. Okay, and it acts on wave function or state of the system. Okay, so let us recall that in quantum mechanics, every physical quantities are very physical measurable quantities. So like the physical measurable quantities means like position, momentum, energy. Okay, so these physical quantities are described by operators. These physical quantities or we can replace the physical quantity in terms of operators. The operator must be linear and hermitian, which acts on a wave function. For example, so a general operator. For example, if I want to say this A is an operator, so first we should represent with a cap, and this A cap operates on the wave function psi of x, which gives another function. It may be phi of x. If I want to say this A cap is a quantum mechanical operator, this must be a linear operator and also a hermitian operator. Okay? This operator is generally operating a system. This A cap is an object which operates in a system psi of x. For example, let's see. Minus I x cross go by dou x is also an operator. So this is a momentum operator. When this operates on this wave function, for example, my wave function here is x square, which operates on this x square, which gives minus I x cross 2x. So this 2x is another wave function, another function which comes after operating this minus I x cross go by dou x. If I want to say this minus I x cross go by dou x is my quantum mechanical operator, it has to satisfy it must be a linear and also hermitian. Okay. Let us see some. So we know that every classical observables have some corresponding quantum mechanical operators. So what are these measurable quantities and how to replace that measurable quantities in quantum mechanical operators. Okay? See. Okay. So let us see how we have to operate and how we have to replace these observable quantities in terms of the operators. See, for observable, I am going to write first position. Position. In classical form, the position can be represented as an x. Okay? The position can be represented in terms of x, right? In quantum mechanics, this x can be replaced into a x cap. That means, if suppose this is a function f of x, this x cap operates on this f of x. Just means you are multiplying this x cap into f of x, which gives x into some other function. It may operates f of x into f of x. Okay. Next. For the next momentum. So the momentum is represented in classical form as p. If suppose the momentum of a particle is along x-axis, so we are represented with p suffix x. If the momentum is along y-axis, we are represented with p suffix y. If the momentum is along z-axis, we are represented with pz. Next, these corresponding quantum mechanical operators, this px is minus i cross dou by dou x, and this py is minus i cross dou by dou y, and this pz is minus i cross dou by dou z. Okay. Next, see, that means, so for example, this is my function x square. If minus i cross dou by dou x means this operates on this function which gives minus i cross into 2x, right? So just we are writing left side. So operator is always operating on the system from left side. Okay. So after operating this function, you get some other function. Next, see, energy. So if a particle moving along x-axis, so definitely it has a position momentum along x-axis. If this particle is free from external field, so it has only a kinetic energy, right? If suppose there is no any potential energy for this particle is free to move along x-axis, then the kinetic energy of the particle is, so kinetic energy kE, since I am writing kE, so this represents the kinetic energy, and this kinetic energy can be written as p square divided by 2m. The particle weighs in 3-dimensional, so you can represent it with p square by 2m. Or we can write this also as px square plus py square plus pz square divided by 2m. And this p square, this kinetic energy is an observable quantity, which is measurable quantities in classical mechanics. So this classical form can be replaced into quantum mechanics operator form as C. So p square, we know that p is minus i cross dou by dou x, and another one p square means again you have to multiply with minus i cross dou by dou x. Then minus into minus plus I into I square, again minus 1. So x cross into x cross square. So dou into dou by dou x into dou by dou x, dou square by dou x square. So this is my momentum operator for p square. If it is along px square or px, so we are writing denominator x square. So if it is along py square, we will get dou square by dou y square. If it is along z square, it is dou by dou z square. So next we have to replace this as is equal to 1 by 2n into, so minus h cross square dou square by dou x square minus h cross square dou square by dou y square and minus h cross square dou square by dou z square. If we take minus h cross square as common outside, so then we get minus h cross square by 2n into dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Right? Next, so we can also write this. See, minus h cross square divided by 2m into, see, dou square by dou x square plus dou square by dou y square plus dou square by dou z square and become Laplacian operator. So that we can write this del square. So the kinetic energy operator in quantum mechanics is minus h cross square by 2m into del square. So this is always a kinetic energy operator in 3 dimension. If a particle moving in a 3 dimension, we have to operate this. To find the energy of an operator or the energy of the particle, we should operate using this expression. Next, so Hamiltonian operator. Hamiltonian operator. If suppose a particle moving along an x-axis or y-axis or z-axis are both in 3 dimensional, if this particle is free, then the total Hamiltonian H is equal to only a kinetic energy p square by 2m. If suppose means if the particle is moving along in some, for example, it is x-axis, then px square by 2m. If the same particle is moving in both x, y and z axis, so the Hamiltonian operator H is p square by 2m. P square means px square plus py square plus pz square. But if this particle is free from external field, so it is always free. Okay, so then the Hamiltonian operator H cap is, you know that p square means minus h cross square divided by 2m into del square, the particle moving in 3 dimension. So this is an Hamiltonian operator. If suppose the same Hamiltonian operator, if the particle is some external field, if this particle is placed in some external field, definitely it has some potential energy. So then the Hamiltonian operator is represented. We know that Hamiltonian is nothing but total energy, that is kinetic energy plus potential energy. If it is in 3-dimensional motion, we can simply replace x into r. Then the Hamiltonian operator is H is equal to minus h cross square divided by 2m del square plus p of r. So this is my Hamiltonian operator if a particle moving in 3-dimensional motion with some external field. Suppose this is my particle. If I place this particle into external electric field, so then definitely this particle has some potential energy. So we have to add the potential energy here. Okay? And the next, energy can also replace it. You know that this is, suppose E is energy. This energy is a measurable quantity in classical mechanics. This classical mechanical observable energy can replace it into a quantum mechanical operator as IH cross rho by 2. IH cross rho by 2. Okay? So this is an energy operator. And so let us see angular momentum. So angular momentum. Angular momentum components. So in classical mechanics, we know that angular momentum L is equal to R cross P. Right? So this angular momentum is also observable quantity, or you can call it as measurable quantities. And this R L is equal to R plus P is an angular momentum. In classical mechanics, this angular momentum can also be written as E1, E2, E3 of the unit vectors, and our component of R is we can call this as X, Y, Z, and the P is Px, Py, and Pz. The component of P is Px, Py, Pz. So it's a cross product. So cross product is represented in terms of determinate form, right? And the solution for this is, if it is in along the x-axis, so the angular momentum along the x-axis is after x, right, y after y we have to write z minus z py, and ly is equal to after y we have to write z, p after z we have to write x minus x pz, and Lz is equal to After z, we will write x py minus y into px. Next, in quantum mechanics, these equation, this angular momentum equation will replace with, see, y into, and the pz is the momentum operator. So pz is minus I cross dou by dou z. Next, minus z into py, again minus I cross dou by dou y. If you take this minus I cross both sides from this here and here, so then you get minus I cross into y dou by dou z minus z into dou by dou y. So this is an operator, angular momentum operator along x-axis. If you want to calculate an angular momentum along x-axis for a particle, we should operate this equation, this operator. Minus I cross into y dou by dou z minus z into dou by dou y. Next, for Ly, see, in quantum mechanics, Ly is equal to, so this is Lx. Ly is equal to minus I cross z into dou by dou x minus x into dou by dou z. Next, Lz is equal to minus I cross x into py dou by dou y minus x, so see, y into dou by dou y. So this is an operator along x-axis, angular momentum operator along x-axis, and angular momentum operator for y, and angular momentum operator for z. That means in a particle moving along x-axis, if you want to calculate a particle along y-axis, you have to calculate a particle along z-axis, you have to use these operators, angular momentum operators. Okay. Next, see, but in classical mechanics, the scalar product are commutative. That means r dot p is also equal to p dot r. But this is not in the case of quantum mechanics. That is, r dot p is not equal to p dot r. Okay. So in classical mechanics, these observable quantities like position and momentum are commutative. This r dot p is equal to p dot r. But in quantum mechanics, it is not in all cases. So r dot p is not equal to p dot r. It may be some cases, but it is not in all cases. Okay, we don't write like this. Next, so in quantum mechanics, if we want to use an operator, it has to satisfy some conditions. So not all the operators we are using, it is not possible to use all the operators in quantum mechanics. It has to satisfy some conditions to use this operator as a quantum mechanical operators. So what are those conditions? See, the conditions to satisfy the conditions for an operator to use in quantum mechanics are, so first, it is linear. The operator must be linear. Next is the linear operator, and it must be hermitian. Hermitian operator. The operator must be linear and also hermitian. So what is this linear operator? What are the conditions of this linear operator? So when you have to say this operator is linear, see, a linear operator is satisfied. A linear is one which satisfies. It's satisfied. For example, if A cap is a linear operator, it is satisfied. For example, if A cap operates on some constant which is multiplied with some function f1 of x, plus if B is some constant which is multiple of f2x, so then which is equal to, you have to write A into A cap f1 of x plus B into A cap f2 of x. If for me it is possible to write this operator A cap in terms of like this, so then only you can say this A is a linear operator. This A is a linear operator. Next, that means if suppose A operates on some constant into the function f of x, so it is equal to A into A cap f of x. Then only you can say A is an operator. Otherwise, if A cap operates on f1 of x plus f2 of x, which is equal to A cap f1 of x plus A cap f2 of x. So then only we can say this A is a linear operator. So next, coming to second condition, hermitian condition. So hermitian operator, hermitian. So we know that hermitian matrix means if A is equal to A diagonal. A diagonal is complex conjugate transpose. That is A is equal to A star transpose in matrix form. In operator form, this hermitian operator form. See, if I want to say this operator A is an hermitian, it has some condition, that is. So let us see. For example, in general, if suppose A operates on, if A operates on some function psi of x, let us see, obviously it gives some other functions, right? So let us take the function as a phi of x. Okay? So if a particle moving along the x-axis, the complete information of this particle is minus infinity to plus infinity over all space, minus infinity to plus infinity. Next, see, if I want to say the hermitian conditions, if suppose this phi of x, take this complex conjugate of this phi of x, that means phi star of x. Complex conjugate of this phi of x is phi star of x. Right, I'm writing this area and psi of x. So these are all these I am studying along x-axis only. So it is based on this single in one direction along x-axis. So if I want to say this A cap is an hermitian operator, then this is equal to integration minus infinity to plus infinity. So I am going to replace these functions. That means psi star of x, A cap, again phi of x into dx with complex conjugate. So if it is possible to write like this, if the left hand side equation is equal to the right hand side equation, so then only we can say this A is a hermitian operator in quantum mechanics. Okay, in matrix form, A is equal to A diagonal. In operator form, you have to satisfy this condition. Okay. For example, if suppose if I replace this A into minus IH cross dou by dou x, is momentum operator. If this momentum operator is a hermitian, then we have to write minus infinity plus infinity phi star of x. For example, this minus IH cross dou by dou x operates on some function psi of x, it gives phi of x. Then multiply the this complex conjugate phi of x into the operator is minus IH cross dou by dou x into psi of x. dx. Psi of x into dx, which is equal to integration minus infinity plus infinity. So psi star of x minus I across dou by dou x phi of x dx. If it is possible to write like this, then only we can say this minus I across dou by dou x is an hermitian operator. But you should remember, all quantum mechanical operators must be linear and also a hermitian. This is the main condition. In the next class, we will discuss in details about the hermitian operators. The eigenvalues of the hermitian operators must be real, and the eigenfunctions of the hermitian operators are orthogonal. So in the next video, we will discuss in detail about the hermitian operators. Okay. So this is about the postulates-2, which tells about the operators in quantum mechanics. Okay. The main condition is here. The main conclusion or summary is, so these all measurable quantities, all measurable physical quantities or observables are replaced into a quantum mechanical operators. These quantum mechanical operators must be linear and also a hermitian. What are those observable quantities? Position, momentum, energy, angular momentum, linear momentum. These are all observable quantities. These observable quantities are replaced into their corresponding quantum mechanical operators. But these operators must be linear and also a hermitian. Okay.